Good morning. Today is Thursday, February 13th, 11 a.m. This is CS 797K Advanced Topics in Data Storage, Lecture 7 on Galois fields and RAID 6. So, this is our course outline. So, we are right here, block based protection. So, we are discussing our Reed Solomon complex coding now. We have finished our basic parity bit protection, basic RAID, diagonal RDP, RAID RDP and stuff. So we are right here. So building Galois field 2 power 3 times table using uh, a primitive polynomial x cube plus x square plus 1. So we have just discussed it in the last lecture, how to build the table. So it's simple, x cube plus x square plus 1, just substitute 2 in place of x, 2 cube plus 2 square plus 1, 13. That's denoted in binary and hexadecimal. So let's remember, um, 5 times 3, 3 times 5 is 2. Okay. So we are just reviewing from the last lectures. Choose a primitive polynomial. There are two for Galois field 8. These are the two primitive polynomials we have, and we'll just plug in 2 in place of x. We'll get 11 and 13 for both of the primitive polynomials, and calculate powers of 2 mod 8, because we are considering 8. So 2 mod 8 by first line with n equal to 0. By definition, 2 power 0 is 1. For remaining lines, shift left 1 bit. That's like just multiplying the it with 2. And if the result exceeds or equal to 8, then just XOR with the polynomial. Okay. So how does that work? So here, log 0 is undefined in any system. So log 0 is undefined for anything. So this is true for real numbers, for g of p, and for g of p power n. Antilog is unused. So here, antilog is also unused in g of p power n. It duplicates antilog of 0. This means logs in Galois field are mod of p power n minus 1. So, so it's simple. Like if we have like 8, we'll just have like, we'll just use 7, for example. Who is paying attention? In Galois field of size 16, logs are mod. Anyone? 16. So it should be less than 16. So minus 1. So the answer should be 15. Yeah, 15. So if it's size 8, logs are 7. It's 256. Yeah, it's 255. So it's 1 less than the number, because we are not using log of 0. So 0 is undefined in any real number. So now building Galois field 2 cube for x cube plus x square plus 1. Again, we have this formula, antilog of log of 5 plus log of 3. So log of 5 is 3, log of 3 is 5 from the table we have just saw from here. Log of 5 is 3, log of 3 is 5, or from this table. Log of 5, yeah, 5 is 3 and 3 is 5. So if we add that, that's 8. So 8 mod 8 is 0. So antilog of 0 is 1. Again from the table. Now, because antilog of 0, 7. We are doing it with 7 because 8 minus 1 is 7. We are just using 7 numbers. So 8 mod 7 is 1. So antilog of 1 is 2. Okay. So logarithms in Galois field of 8 are modulus 7. It's 8 minus 1. So we'll just do mod 7 So if its Galois is field 8, so we'll just mod the numbers with 7. So if it exceeds 7, we'll just mod it with 7 and cut it off to the numbers and then multiply that in the next iteration. So 5 times 3 antilog of 1 is 2. Therefore 5 times 3 is 2. So here we are comparing p of x with p of x, that's x cube plus x plus 1 with x cube plus x square plus 1, because these are different polynomials, primitive polynomials. So do you have different tables for different primitive polynomials? Yes. Yes. So this is how we built it. So one, we'll just duplicate 2. It's, I mean, double 2, 4. We'll double 4, 8. So we'll 8 and XOR it with 11 because it's greater than 7. We'll get 3. We'll 3 times 2, 6. 6 times 2, 12. We'll again XOR it with 11, get 7. And 7 times 2, 14. 14 XOR 11, 5. 5 times 2, 10. 10 XOR 11, again 1. So it repeats again. So it's n, it's 2 power n. And what about log n? So for example, for 2, we have 1. So for 2, it will be 1. And for 3, it's 3. For 4, it's 2. So it will be 2. For 5, it's 7. So it's 5 here. 7, 7, it's 6. For 6, it's 5. Four is 6, yes. 6. For 6, it's 4. For 5, it's 7. So it's 6. So on. So we'll just like use this number to find log of n. We'll use 2 power n to find log of n. Same x cube plus x square plus 1. If we build, so there will be slightly different numbers coming here because we are XORing it with 13 instead of 11, because if we substitute 2 over here, we'll get 13. So we are XORing it with 13 if it exceeds 7, because its Galois field 8. 8 minus 1 is 7. So in the same way, we built both the tables. So there are different numbers. So the tables will be different again. So if we see here, so the latter half is getting changed, this thing. So whenever it's XORing, it starts XORing, it gets changed. The numbers gets changed. So the latter half of the part will be changed. You can see here the difference. So that's the difference. So we have different values for different primitive polynomials, even if we take the same Galois field. It's non-primitive polynomial fail. Yes. So what if we take non-primitive polynomial instead of primitive polynomial? Sorry. So this is a non-primitive polynomial, x cube plus x square plus x plus 1. So that's 15. So we will XOR it with 15. So if it is equal to or exceeds 7. So 0, it's 1. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 XOR 15 is 7. 7 times 2 is 14. And again 1. It wrapped up too early. Okay, so if it's not a primitive polynomial, it wraps up too early. So that means we are missing some values in our table. So if we plot a table using these values, for 0, everything for 1, so we have a lot of missing values, right? And we don't have 1. I mean, we don't have inverse for everything, and there are a lot of missing values because it wrapped up too early. So that's the problem with non-primitive polynomials. So that's why we are considering primitive polynomials. It's Python time. Students download table builder.ipython from. Okay. So it's your task. Just open your Blackboard and download gf table builder.ipython from Blackboard now. So let me know if you downloaded it. Meanwhile, I'll open the as well. Let me explain what's in the IPython notebook first. So we are generating tables. So we are generating log tables using these power 8 and polynomial 11D. So global GF table sizes. The size is 1. We are just doubling it. We are left shifting the power. That means we are just multiplying the number with 2, and we are printing the table. So initialize. So this is how we initialize at the very first of 0. And for range of b, I and b, we are left shifting and we are XORing it with the polynomial. If it exceeds, if it's greater than 7, yes, and then returning the GF log and GFI log, that's anti 2 power n and logarithm and anti-logarithm table. And dump table, so what does it do? It just visualize everything for us, how the table looks. This GF log, GFI log generate table. So we'll just give a polynomial here, the values here to generate our table. So this is how the table was generated, GF logs and I logs. So we can print the table size, it's 8. So if it's not it's a non-primitive polynomial, it will be less size, but it's a primitive polynomial, so it's 8. And if we try to look at our table in a vertical manner, so it looks like this. So dump log a log, and for I in range 0 to GF, so it checks to prove the table really are inverses of each other. So every number has an inverse or not. So it checks. And addition, it will do the tasks. I mean arithmetic tasks by adding, multiplying, subtraction, and division. Here we can see how we did that, and print a portion of GF multiplication table. We'll just print the table with the table we just built, log and anti-log tables. So this is how it looks. So like everything we discussed, we are just doing it in IPython notebook. So bad GF log, bad GFI log, generate table 315. So this is the one we built for bad table. Okay. So 3 comma 15. So it just wrapped up too early here. 1, 2, 3, 4. So if we print the size, it will be like 4. And it's repeating again. So if we print a table, a lot of undefined values will be in the table. So will 2 power 3 using PP 11 or 13 come from the multiplication table matches? Try building with some other PPs, see how it fails. Comma 15. So you can do that later, I guess. Primitive polynomial characteristics. So what is a primitive polynomial? So what are the characteristics of a primitive polynomial? We are discussing a lot about primitive polynomials, but what are they? So a primitive polynomial is an equation of the form a x power n, b of x power n minus 1, and so on till 1. So where b, f are between 0 and x minus 1, that's 0 or 1 for binary. So must start with x power n, the size of Galois field. So alternatively, that the a coefficient must be 1 here. First term in GF 2 power 3 is x cube. Why? Because XORing that bit off is how we wrap back to into the field. So must end with 1. Why? Because otherwise we would never wrap back to an odd number. Must generate a complete log anti-log table. Why? Because without it we can't make a complete multiplication table, right? Yeah. So this is the stuff we just discussed about, but this is how a primitive polynomial looks like. So this is the equation. So a must be always 1. So it's just like x power n. N should be the a coefficient must be 1. This is 1, and the first term 2 power 3 is x cube because XORing bit of wrap up too early. So this is the equation for primitive polynomial. And it must meet these conditions. So we can find primitive polynomials in many links, which I'm going to provide you later. So representations of polynomial, GF 2 power n as polynomial, as binary, as hexadecimal, as decimal. So for everything here, we can see like 3, 2 is 0, 1 and 1. So x cube, x squared term is 0, x power 1 and 1. So 1, 0, 1, 1. So x power 8 is 1, 7, 6, 5, we got zeros. So these 3 zeros, 4 is 1, 3 is 1, 2 is 0 again. So 1 and 1. So, and again here, x power 8 and 3 zeros, 4, 3, 2, and there is no x term. So it's 0 and 1. So I guess you know how to convert from binary to hexadecimal and hexadecimal to decimal. So it's easy. So just take a polynomial and you can easily convert it into binary, hexadecimal, and decimal. So that's how we represent polynomials in binary, hexadecimal, and decimal. Remember to think of the polynomial as changing the modules to allow complete exponential cycles to exist. List of irreducible polynomials up to GF25664, that's 2 power 8. So if we open the link, we'll have a list of Galois field polynomials right there. So irreducible P of x. So these are all the primitive polynomials listed until 505, 2 power 8. So you can see the list of polynomials you can use to build your Galois field tables. So that's the link provided here. Primitive 255, went back to n equal to 255. Okay. To RAID 6, so students seek a more detailed explanation of what follows or invented to read the paper. So if we open this paper, it's about RAID 6. So if you are interested to read the paper, so you will get all the math in this paper. We'll just discuss the equations. So what's the math behind the equations will be in this paper if you are interested. It's not completely accurate, but it's good enough to know what's going on behind the equations. So here, if in GF 2 power n, addition is the same as XOR, we know that. Subtraction is also same as addition too. So in XOR, both addition and subtraction yields the same results. So XOR is thus a basic GF 2 power 1 p parity. So this is the p parity. So D0, D1, D2 until Dn will XOR all the what's that way say data blocks in a parity to get a p parity. So in GF6 we have p parity and q parity. For p parity we'll XOR everything to get a p parity, and q parity will be obtained like this. So g power 0 times d0 plus g power 1 times d1 and so on. So we'll get q parity calculated till n minus 1. It's n, so n minus 1. So g means minimum primitive elements are minimum generator are for binary just 2. So we'll see the equation q parity, g0 d1 and so on. What is the maximum number of data drives? Data drives, so number of data bits plus 2, because we have p and q parity as well. So data drives, yeah, is plus 2, yeah. So maximum number of data drives is, yes, Galois field minus 1. Again, 2 power n, maximum number of drives is 2 power n minus 1. And label these drives d0 to dn minus 2. N minus 1 would have identical multiplier to drive 0. Maximum number of drives in a volume, that's 2 power n plus 1. Yes. And what value would you choose for n? So we can choose any number of values for n. Okay. Number of drives limited by size of Galois field. So 0, 1, 1 square 2, 2, 2 double 4, 4 double 8, and by XOR it gets 3, 3 double 6, and so on, like we just counted. So with GF 2 power 3 field, we are limited to 9 drives, 7 data, 1 P and 1 Q, total gives us 9 drives. So with GF 2 power 4 field, we are limited to 17 drives. So that's 15 data drives, 1 P and 1 Q, total gives us 17. And 2 power n, in the same way, it's 2 power n minus 1 data drives. That's the formula we get to calculate number of data drives. Now, a GF of size 2 power 3 can only do math on values between 0 and 7. This means the calculation must happen 3 bits at a time. It is possible using bit masks to do math on large chunks, but our sample code does not do that. We can do math between 0 and 7. Yes, in Galois field 2 power 3, we can just do math between 0 and 7. Yes, this means the calculations must happen 3 bits at a time, because 7 we can represent it with 1, 1, 1. So just we can just use 3 bits of math. So we can use bit masks if we need to use a larger bits. I mean, if you need to use 4 or 5 bits, you can just use the bit masks to do your calculations. So reconstruct cases. So what if a single drive failure happens in a RAID 6 DP volume? So for example, P is dead. Out of all the drives, the parity P was dead. So we can easily rebuild using the data drives. We can XOR all the data drives to get the P. So dual drive, or if Q is dead, we can easily rebuild using GF algebra. So how we just built Q in the very first place, we can do that because it's just a Q dead. It's a single drive failure. So we can easily reconstruct P and Q. What if dual or DX dead? So we can also rebuild that using parity P and the left of the rest of the drives, and we can reconstruct a single drive failure. And double drive failure if both P and Q are dead. So both parity Q and parity Q, I mean P and parity Q are dead. So parity P can be constructed using XOR function for all the other data drives. So reconstruct separately from data drives. We can also reconstruct Q with the data drives as well. So that's how we did in the very first place. What if D, X and Q are dead? So one of the data drive is dead and parity drive Q is dead. So we can reconstruct DX from P. Yes, we can use the P drive and the other data drives to rebuild our dead drive. And we can just rebuild our Q drive again using all the rest of the drives. So DX and P was dead. So one parity was dead and the P parity was dead and DX was dead. That's one of the data drive was dead. So that's a little complicated. So we use Q syndrome to rebuild DX, then generate P. So what's Q syndrome? We are going to see what is Q syndrome. And if two data drives were dead. So P was alive and Q was alive, but two data drives were dead in the RAID. So we use Q and P syndromes and the distance between X and Y to rebuild DX, then rebuild DY from the other data drives plus P. So we'll just use the distances to get our DX and DY back. So that was built from the equations which we are going to show. And if you want to see the math behind the equations, you can very well go through the paper that was in the link. So reconstruct DX and P drive. So compute QX. So Q parity assuming DX is all zeros. QX is Q syndrome. So we are computing Q syndrome. So assuming DX is all zeros. So the dead drive, we assume it 0. So it's like ISBN. We're assuming 1 is 0 and we are just recalculating by using the mod. So how we done for ISBN, we are just doing the same thing for the data drive in RAID as well. So Q parity assuming DX is 0. So QX plus G power X times DX equal to Q. So G power X times DX equal to Q plus QX. Remember with XOR, minus is really plus. So subtraction is really addition. So we'll just use the GX, send the GX to RHS to get the equation Q plus QX by G of X, and it's like multiplying G power minus X. So this is how we compute Q syndrome. Okay, so QX, so this is Q. So let's see what happens. So compute Pxy and Qxy. So reconstructing two dead drives, dx and dy. So two are dead, two drives are dead. So the first step is assume all the drives are dead drives are 0, and then use the equation P syndrome and Q syndrome. So algebraic magic you can really see in Evin paper. So this is the final equation we get from the paper. So dx q plus qxy times g power minus x plus pxy times g power y minus x divided by g power y minus x plus 1 in the braces. That's an integer value 1. We're just adding it to g power y minus x. If we pre-compute magic multiplication tables A and B, we get, so there are some magic multiplication tables that's provided in the paper. So we use those tables to recompute A and B. So dx here q plus qx plus it's g minus x, we are making it b, and this term we are making it a. So g minus x by g y minus x plus 1 is b, g y minus x by g y minus x plus 1 is a. So we're simply multiplying b and a to get dy. Again we're doing p plus pxy plus dx. So this is how we get a and b from these equations. Next, magic multiplication table. So dx equal to q plus qxy times g power minus x by g yx plus 1. So this is the magic multiplication table we get, and we get the values of a and b. We just saw the values of a and b, how we substituted here. This term by this term is b, and this term by this term is a. That's the same thing here. So basically we can pre-compute multiplication tables for all possible combinations of double drive failures. Trading space for speed. If GF 2 power 8 is GF 256, 2 power 8 is 256. How many drives does this allow? So 256. So it's 255 plus 2. So it's 257 drives in total. So including parity P and Q. So primitive polynomial 2 power 8 plus 2 power 4 plus and so on gives us 11D. Generator is 2, of course. Can repair any 2 missing drives. So can detect and repair 1 corrupted drive. Can detect but not successfully repair 2 corrupted drives. So what is the Hamming distance of RAID 6? It should be 4. 4 minus 1 is 3. It can detect 3, but it can just repair 2 drives. And Python time. So you can follow along. We'll see the code for RAID 6. We're using the same generate tables code again. We just saw in the last IPython notebook file. We can just dump the table, qdump. So log and ilog. So let's run the code. See, so that's just the definition. So we don't have output. We are generating table for 8, 258. Okay, ilog and add dialog of generate tables 8, 258. It's 256. So dump the tables. So we'll see how the table looks like here. So it's a large table. We just dump the table, and we can just print the size of the table. It's 256. So we have 255 values there. So we can just print, or we can just format it. It's just the formatting. So we can see where it wrapped. 1, 2, 4, 8, 16, 32, 64, 128, 29 again. Yeah, 58, and 116. And here, what does this say? A check to prove the tables really are inverses of each other. So every table should have inverses. So g of log is 0, 0, but g of log is 0, 1. So RS function by Python, use Galois fill to power n. Addition is always a simple XOR. So it's again doing operations. Yes, and print a portion of the GF multiplication table. It's printing a portion of multiplication table here, there. So we can use see the table and find the inverses as well here. On, if you can see, and number of drives is 4, block size is 5. So we are just constructing a GF6, so RAID 6. So there are 4 drives here, and from the 4 drives we are building a P and Q parity, and we are generating a complete table. Let's see. So number of drives are 4, block size is 5. So this is the simple construction of RAID 6. Okay. So P and Q parity drives, 0 times block size, Q is 0 times block size. We're just initializing it with zeros first, and then calculating P and Q parities from this code, generate P and generate Q. It's just XORing the things, and it's just adding GF multiplied drive DI drive Q of I from the equation we have discussed in the slides. And now we're dumping all the drives to see how that actually looks. And we can, so this is the drive. So in each drive we have these values. We also have parity P. So it's just the XOR of these to get this XOR, and we have Q from all the other values as well. So we'll fail and reconstruct P drive. So we'll just make P drive to zeros. And how do we reconstruct? We'll just XOR these things to get the P. That's it. So we are failing it. So now see the P drive is having all zeros, and we can reconstruct it by XORing. So show the difference between G of log, I log, and inverse G of log. So this is G of, this is n, this is the numbers, and G of log n, I log, anti log, and 1 by G of I log of n. So it's the inverse. And fail and reconstruct drive 2 and the parity P. So we know how to reconstruct P, and now we are failing drive 2. So we'll just we have reconstructed P. So we are failing 2 drives here. We just can't reconstruct P or 2. We need a P syndrome to reconstruct our drive. So we'll assume all as zeros and use the differentiation form, difference formulas and everything. So let's see, we are just failing 2. So here we have zeros in P and zeros on drive 2. Okay, so rebuilding drive 2 byte 0. So here in the code, we are rebuilding everything. GF multiplication table, partial 1Q and inverse. So the inverse we have just saw in our table. So we'll reconstruct drive 2 using the equation that's in slide. Now fail and reconstruct 2 data drives. We are reconstructing 2 data drives. So we'll consider 2 syndromes now. Out of failing drive 1 and 2, we have these values 1 and 2, and we are reconstructing it here, and we can see the reconstructed table here. That's with the equations, and that's described in the Python file with the partial sum by syndrome of both missing drives. This eliminates the second drive and leaves the first, so on. Generate GF advisor that sums the 2 missing drives. So this is how we have it in IPython notebook. So if you are not getting the equations from here, you can just simply go through the code. We have every code written over there, so you will have an idea like how we are rebuilding it in the IPython notebook. So it's easy for you to understand. Let's see. So for the quiz, you need to work on the IPython notebook file and fill in the answers. We'll see it at the end. Yep. So RAID 6 PQ versus RAID DP. So what's the difference between RAID 6 PQ and RAID DP? So that has diagonal parity, that means rotating parities. And in RAID 6 PQ, we have two parity bits, P and Q, which are not rotating. That we have given a separate data drives to P and separate data drive to Q. But in RAID DP, we have diagonal parity. It's rotating parity. So very rough analysis, right? Hotspot parity drives, RAID 6 P and Q rotate like RAID 5. P and DP did not historical rotate, but there's no reason for them not to. So in RAID 6 PQ, so there are different approaches, different people came up with. So instead of giving a separate data drives for P and Q, they have made it rotating like a diagonal parity. So detecting corruption, RAID 6 PQ can find data corruption by recomputing P and Q, ISBN like nature. Missing diagonal stripe means not every data block is covered by DP drive. So at the time of building the RAID 6 PQ, they will just program it hard code program it to recognize which is the parity bit of P and Q in the given data drive or in the given stripe. So that's how they construct this diagonal parities for PQ as well. So degraded performance, any data drive failure requires reads to hit all remaining data drives. DP recomputes double fail stepwise. Some block reconstructs faster than others. PQ recomputes double fail with lots of matching. So we have geometry limitations like number of data drives in RAID DP must be one less than prime number. Yes, however, this is workaround. RAID 6 PQ limited by the size of the Galois field, but no one have ever asked for 100 drive wide volumes. PQ easier to implement in hardware. So the number of, if we increase the number of data drives, obviously our read and write functions will be more fast. So there is no one ever built 100 drive wide volumes. So it's not a actual limitation, but someone have out there done it for, you know, fun, but in reality, no one has ever done more than 100 drive wide volume. So PQ easier to implement in hardware. Yes. Now some had too much time on their hands. Okay, let's open one of the links. And here they have done anti-log table for GF256 with irreducible polynomial 283. So they have taken the primitive polynomial and minimum primitive elements, and they have constructed all of these things. I mean, they have constructed for each and every primitive polynomial out there and build the tables. So yeah, that's what we just has created in our code table as well. So we can just copy paste the code output and build a separate web page like this. We can also check these values from our code as well. So 30 irreducible polynomials for GF256. You can see in this link primitive polynomial and irreducible polynomials. So again, here we have irreducible polynomials in decimal, hexadecimal, minimum primitive element and element in decimal. So you can go through this if you are interested. And testing GF256 multiplication. So from RAID 6 .ipynb file, partial multiplication table show. Let's open this. Python. This one, not this one. RAID 6. So from RAID 6.ipynb file, partial multiplication table shows 0 times 0d times 0, 11, 0d Cody plan log table. Just a second. Oh, lot of references. So the bottom line here is it's the same as all the raids we discussed till now. We have RAID 6 with two parities, parity P and parity Q. We can reconstruct the two failed drives out of parities using the equations we have in the slides. It's not like simple XORing things, but we have equations which if you are interested. So the bottom line is to get know how the RAID DP or how the RAID PQ works. So we have two parity bits P and Q. P is the XORing of all the data drives and Q will be obtained by the equations. And if two of the data, if one of the bit was failed, we can easily reconstruct. If P was dead, we can just XOR the things to get P. If one of the data drive is dead, we can just XOR the P and remaining data drives to get the data drive. If two of the data drives fails, then comes the complex thing to do. We have equations. We'll build. We'll assume it as 0 and we'll use the formulas and we'll reconstruct those two drives. So that's the bottom line. So and again, instead of P and Q in separate data drives, so the engineer solution is make it rotating. So the two parities are rotating now in the data parities are RAID. So instead of making a separate block for P and Q, they are making it rotating for all the things like RDP, diagonal parity rotating. So they are just doing it for the rotation of P and Q. And these are some of the references you can go through. Some GF log and anti-log tables. We know how to build log and anti-log tables. So there is some course notes over there. Irreducible polynomials, Galois field calculator. We have calculated. We know how to calculate Galois fields. So multiplication table, RAID 6 GF discussion, Anwin paper. So the main focus here is understand how the PQ works, understand like we can reconstruct two failed drives and get to know the math, like how to construct Galois fields, what are primitive polynomials, the list of primitive polynomials in the link we provided, and try to build a multiplication tables for that, a log and anti-log tables as we discussed, and those are some easy stuff. So if you really want to concentrate on math behind the equations, you can go through the paper in the very first slide and you can get the math. And yes, I guess we're good for today. So it's basically complex code because if you want to know the equations, it will be complex. But if you understand the outline of how the RAID works for PQ, then it's not that complex. But if you really want to go inside and look at the math, you can do that. But we don't have any questions on mid and end term for the math behind the equations of RAID PQ. Yeah. But we do have questions on Galois field, log and anti-log tables, and the multiplications and multiplication tables and stuff like that. That's what we discussed earlier. We have also discussed it on board as well, how to do the things. We have also discussed ISBN, which is the concept we used here, like substituting zeros if one of the drivers failed and then reconstructing it using the other drives. So that's what we have discussed in ISBN as well. So if you know those concepts, so those concepts will be asked in the exams and you can easily answer. But using those concepts, that's the math built behind these equations. Okay, that's the thing. Now you need to use your IPython notebook files in the Blackboard downloaded and answer your quiz questions. I have not built this quiz. Professor Wilner has built this quiz, so it takes long time to finish the quiz. Yeah, but it's yeah. Mm, let me look the quiz. 12 and 13. That's the code for quiz. So to attend the quiz, you need to have your laptop with the IPython file. See the questions. Areas. Attendance. Yeah, it's easy. Dynamic binary. 59 divided with 2 is a 4. 19. 9 is 18. 1. 2, 4 is 8. 1. 2, 8, 16. 2, 7, 4. Yeah, it should be 1. So you should know how to calculate the binary code.